So in the last video, we have examined the evidences for the continental drift theory. So we discussed about what were the lines of evidences that were put forward to support the continental drift theory. For now, we will take a look at the evidence for the seafloor spreading theory. Okay? So, first of all, um, the seafloor spreading theory was again um, discovered because of Harry Hess and Robert Dates, and they started by mapping the ocean floor. So first, I want you to see how the ocean floor looks like if there is no water in it. By the way, this video is from Hubert Heller, so credits to him. But I just want you to see how the ocean floor looks like without the ocean water in it, if we were able to drain the ocean water. Okay, so those are the continents and the ocean floor. So we now start to drain the water, and we can see all of these elevated parts. Those elevated parts are the continental land masses. Then at the middle, so those are the islands. And in the middle of these, you have the mid-oceanic ridge. Okay, so I think it's kind of important that we go back to the infographic he just showed here, which is these are the height of the continents and the islands that poke out of the water, and then the ocean ridges, the mid-ocean ridge, have this height. So it's less than the islands, of course, but they can be called underwater islands. That's why in some books they call it underwater mountains. Okay, so let's play that again. I'm sorry. So this is the mid-ocean ridge or oceanic ridge in the middle of the Atlantic, I believe. It runs all throughout the Atlantic Ocean, and its length is about 80,000 kilometers. We also have the Marianas Trench, obviously near the Pacific and Philippine Sea Plate, and then the East Pacific Rise. And that's how your seafloor looks like. And one important thing to note here is how were the scientists able to do that? By the invention of the technology called sonar. So sonar is like echolocation of bats, but it's done underwater. It still uses sound frequency. So again, because of the World War II, people started inventing submarines, and submarines, they have to know what terrain they are moving in, otherwise they would, crash onto these underwater mountains. So they had to invent sonar. And again, when Harry Hess discovered and Robert Dietz discovered these mountain ranges, and then they observed them, and then they found out that magma comes out of it, and then obviously they knew about continental drift theory, which was proposed in 1912, so earlier than their time. So they kind of use that to formulate their own theory called the seafloor spreading theory. Okay, so what are the evidences for the seafloor spreading theory? So number one is the age of the oceanic lithosphere. So remember, class, that scientists have techniques to find out the age of these rocks in the crusts. We have radioactive dating, so we look at the radioactivity of the radioactive atoms that are in the crust, and we find out their ages. So here, if you notice, the Neogene period, the Quaternary period is the Quaternary part is where we are now. So where we are, the age of modern human beings. Neogene, Paleogene, Cretaceous, Jurassic, Permian. These are way earlier in the Earth Earth's history. So if you notice at the middle of the oceanic ocean ridge, that's the youngest Neogene period. But then as you go back, it now goes back to the Paleogene and Cretaceous period, right? So you have this gradual aging where the center is always the youngest, center of the ridge. So that's one of the points that are point out. Rocks at the center of the ridge are younger. That's one. Second, rocks away from the ridge are older. So if you look at near the continental shelf here, that's colored light blue here. That light blue is now 120 million years, 110, 120 million years ago, compared to at the center where it's 0 to 10 million years ago. Okay? So rocks at the center of ridges are younger. Rocks away from the ridge are older. So that those are the first two evidences, because those two can only be explained if indeed it's the seafloor is spreading, creating new seafloor. That's why at the center you have younger seafloor, and then at away from the ridges you have older seafloor. Okay, and then the next evidence for that is um, the amount of siltation that the ocean floor has. Okay, so let's recall the class is made up of a layer of basalt rock, granitic rock, soil if it's in a continent. But if it's in the ocean, you will just have basaltic rock, and then you have the equivalent for soil, which is siltation. And again, what is siltation? Siltation are just organic, you know, materials, particles from things that are living. So fishes, they poop, they have decayed parts, and so this organic material, including also things that erosion brings from the rains, settle at the bottom of the ocean. And obviously, it's logical to think that the older the ocean floor gets, the more siltation it will have, and the newer the ocean floor is, the less siltation it will have. Okay, so that is one of the observation. They notice that when you are at the Atlantic ridge, there is less siltation, and then as you move towards the continents, away from the ridge, the siltation becomes thicker. Okay, so again, young rock at the ridges are younger, rock away from the ridge are older. Siltation is thinner at the center of the ridge. Okay, and to illustrate to you this, I want you to look at this video. Again, credits to the owner. This is from the channel Waterlust. Again, I'm just going to mute it. So here it shows you the Mid-Atlantic Ridge, and on the Mid-Atlantic Ridge, it's where the North American and the Eurasian plate diverges, right, at a rate of 2.5 cm per year. And then smack in the middle of it is Iceland. Okay, the ridge passes directly through Iceland, creating a crack on the Earth. I kind of disagree with this statement because this, again, I'm not. I'm just pointing out some things that are that I know. So this suggests that Iceland was there, and then the ridge simply fell in between Iceland. That's why Iceland broke into two parts. But from what I know, Iceland actually sits directly underneath a hotspot. So the Iceland landmass is created by a hotspot. So you could even probably say that maybe it's the hotspot underneath Iceland that causes the divergence. So so while this statement kind of tells us that the island was there and then the divergent boundary came, that's why the island is now split. that other perspective that I'm telling you is the case where there's just simply a hotspot, and then that hotspot created the divergent boundary and the volcanic island that we call um, uh, Iceland. Because remember, hotspots are very, very strong sources of magma, so that's why it creates that island. Okay, so it passes through Iceland, and then when these cracks get filled with uh, water, this they create this. Look at how clear that water is, right? So why is that clear? Well, number one, because it is newly formed crust, and again, newly formed crust do not have a lot of siltation. Okay, and probably it's also a contributing factor that it's glaciers that are glacier water. I mean, water from melted glacier that fills in these cracks. But the point is, um, because the crust is newly formed here, that means the crust did not have any sort of erosion yet that would create siltation. No living organisms yet that are trying to, spew off organic materials aside from few mosses here and there, seaweeds. So that's why this is very clear. So again, that's the third evidence presented that um, there is less siltation at the less sediments at the uh, center of the ridge. It's thinner in terms of sediments and thicker as you go towards the continents. Okay. Now, how about a fourth evidence? Where a fourth evidence is about the ages of ocean floors and continents in general. So here, I'm showing you this. Focus on this infographic here. It says here that while continental crust that is billions of years old still exists on the Earth's surface, most oceanic crust is less than 200 million years old. So what does this mean? This means that usually oceanic crust is younger than continental crusts. Okay? So again, if that is the case, then that means the ocean floors are created later. So therefore, they are newer. So again, it supports the fact that there is this process of ocean seafloor spreading. And again, it starts with the continent being, cracked into two and then developing an ocean floor at the center. So therefore, obviously, the ocean floor will be younger than the continental uh, counterpart. Okay. Now, another convincing evidence of seafloor spreading theory is what we call the magnetic reversal or the magnetic stripes that are recorded in the seafloor. But the only problem is before you can understand what this means, I have to introduce to you some concepts of magnetism. Okay, so again, a lot of these things are integrated in science. So forgive me if I have to discuss this, even if this is technically a concept in your second grading. But anyways, here it is. So I have here an animation of a magnet, right? Because we will talk about magnetic reversals later on. I have an animation of a magnet here, and I have here a compass. So if you notice, the red part is north pole, the south part is the white part, and then you have a compass. Well, a compass is simply a magnet that can rotate. So the red end is also north, the south end is also south. So notice if I place the compass here, the shape of where the compass is pointing out changes. And in fact, the red part now is pointing to the red part now is pointing to the left, but oh no, sorry, to the right. But if I flip this magnet, meaning I click here, flip polarity. If I flip this magnet, notice what happens to the compass. 1, 2, 3, go. It changes direction, Okay? Because the basic tenet of magnetism is uh, opposite poles attract. So if I flip this, if this is north, now I flip this so that it becomes south. Now the opposite pole, which is the north, the red one, will be attracted to the white one. So it changes. So what is the main takeaway here? The main takeaway is that compasses would change direction because of the orientation of the magnet. So if I flip this, the orientation of the compass changes. If I flip it again, it changes. Okay? Now, the main thing here is to realize that the Earth class is actually can be considered as a big magnet. The Earth has magnetism in it. So if you are, for example, in the Philippines, I hope you can see the Philippines here. You're living there, so let's put that compass there in the Philippines. That's why Luzon would be your north, because that's how you, when compasses always point to the north. So if this is an arrow, the red part is the arrowhead. So if you're that's why the arrowhead points to to Luzon. So that's why Luzon is the northern part. But the point is, the magnetism of the earth flips. If the magnetism of the earth flips, then the I'm sorry, this animation also flips the planet Earth, but that's not my intention. But I just want to flip the magnetism of the Earth and not the Earth. I did not notice that it will also flip. But the point is, if we flip polarity, the magnetism also, the compass also flips. Okay? So, uh, if I am here, if I flip the polarity, now, slowly but surely, the compass also flips in polarity. Okay. Now I know you have a lot of questions. You have questions like, why is the Earth magnetic? We will discuss that in module and quarter 2. Why would the magnetic field of the Earth flip? Again, we will discuss that in second quarter. But for now, accept the fact that the Earth is like a big magnet and that its polarity flips. Okay, its polarity flips. Okay, so the point is, some time ago, scientists studied volcanoes. And you see volcanoes spew out magma materials. Obviously, they become lava. And then as they spew out lava material, they solidify on the ground. And then a few years into the future, a few million years into the future, that same volcano erupts and again deposits another pile of magma, then another pile of magma. So you have this, not magma, lava, pile of solidified lava, another pile, the next eruption, next eruption, next eruption, next eruption, next eruption. Now, scientists notice that when you examine the layers that are created, you see magnetic crystals in it, magnetic iron crystals. And these magnetic iron crystals are like compasses, right? Are like compasses. And then the compasses, when you examine, they're curious because each layer or layers seem, I mean, in the as they go through the layers, there seems to be a flipping of directions. That means, for example, the magnetic crystal in this layer, they notice that the north of the crystal, of the compass, of the north direction that is pointed by the crystal, which is like a compass, is upwards. The next layer is still upwards, next layer is still upwards, but the next layer, suddenly, it's downwards. And then the next layer, downwards, 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 downwards. Next layer, again, upwards. So scientists noticed that every few million years ago, an average of 100, a few hundred, years, I believe it's 250,000 years. That's the average. The magnetic field of the Earth flips, and that is what is causing the observation in volcanoes in the land. So we are still talking about volcanoes in the land, not in the ocean ridge. But bear with me. Again, this is a long explanation because there are a lot of concepts involved here. So the point is, you have this layer. where the magnetic polarity is upwards, and then the next layers are downwards, then the next layers are upwards, then the next layers are downwards, and so on and so forth. And then we always see the same observation for any old volcano. So, for example, if you have a volcano near Italy and you observe that at this layer it's pointing up, somewhere in other volcanoes in other parts of the world, you always also see uh, that direction. And then when you date, for example, at 230,000 years, what was the direction of the magnetic field? You look at other volcanoes, it's always the same. So that means that these volcanoes that are not connected because they are, far away from each other, the fact that they point a certain direction in their magnetic crystals that solidified at certain specific times, that means it's the Earth that's causing it. That means the Earth's magnetic field is actually reversing every couple of 100 years, 250,000 years in average. Okay? So, we discovered that before we knew about ocean ridges. Take note, that's important because it gives weight and credibility to this discovery. We discovered the magnetic striping in volcanoes, land volcanoes, way before we discovered ocean ridges. Okay? Now, what about ocean ridges? Well, it's the same phenomena, isn't it? Because magma comes out, it solidifies, and so the solidified magma would have certain iron crystals that act like compasses. Okay? And what do we see in the ocean, the seafloor? It's this. So let me play this video for you. So as the plate diverges and then new seafloor comes out, the magnetic field is like that. But as it flips, the magnetic field, the crystal's recorded direction also flips. So the red, see? So after 53 million years ago, it flips. 38 million years ago, it flips. At 9 million years ago, it flipped. 0 million years ago, so it's like that. So here, the blue part represents a magnetic field that where the north is upwards, right? And then after 155 million years, it flips. Now, and then when it flips, the crystals here also flip in direction. Okay, and you have to remember that when magma is still liquid, the crystals are free to move, right? But when they solidify, obviously they get frozen. So therefore, you take a record, a snapshot of what the magnetic field was at that year, or when the magma came out. So as you move through this, you have this pattern of magnetic stripes. Okay, so again, where what happened is in the blue part, the orientation of the magnetic field is opposite the orientation of the other. So it would be um, this would be in one direction, this would be the opposite, just because the magnetic field of the Earth is reversing. Okay, and that is pretty convincing evidence, class, because number one, uh, there's no way that all of those rock crystals would simply align to one direction out of other processes. The only explanation is because of the magnetic field of the Earth. Second, because these things are, when they solidify, they get frozen. So therefore, you take a snapshot of the state of the magnetic field at the time when it solidified, right? So therefore, it gives you a timeline of how many millions of years ago was this part of the seafloor created. Okay, so you create this magnetic stripes, and you notice, class, that it's always a mirror of each other. What do you mean it's always a mirror of each other? So notice here, the how thick the blue band is on the right is also how thick the blue band is in the left. Here you have a thicker band. It's also here, it's thicker. So that could only mean that when the structure on the left or on the right is mirrored in terms of structure sa left, it could only mean that the same structure was created at the center, and then the center split into two. to the left side and the right side. That's why, as this goes on and on and on over time, the right side is always a mirror image of what structure can be formed on the right side. You cannot explain that if you would think of other scenario aside from the fact that the seafloor actually spreads. Okay, so that's pretty convincing evidence, class, of seafloor spreading theory. So again, number one, they looked at the age at the center of the ridge is younger, and then the age at farther away from the ridge is older. That's two. Then three, they looked at the sediments. There is thinner sediments at the ridge, thicker at the near the continents. And then fourth, they looked at the general age of seafloor versus continents. So seafloors are always younger than the continents themselves. So that means they are created um, early, they are created in the near past than the continental crust. And then lastly is this phenomenon of magnetic striping in seafloors. You can actually look at the magnetic crystals in embedded in the crust, and these magnetic crystals act like frozen compasses, and they record the magnetic field of the earth as it flips over millions of years. And again, um, you cannot say what if they just misinterpreted that, sir. What if it's not true that the magnetic field flips? Well, we have to lend credibility to it because again, we discovered magnetic striping in the land, in land volcanoes, way before we knew about oceanic ridges. So therefore, the fact that the same phenomena happens, that means it's not something that was invented just to explain oceanic ridges, but the mechanism for magnetic striping was already established in land volcanoes, and then it just so happened that it could also be applied to explain the seafloor spreading theory. Okay, so I hope that clarifies the the concepts that uh, we're trying to get across, why we believe the seafloor spreading theory is more or less correct because of the evidences presented for it.